Hello everyone and welcome to the CARMA webinar series, Work Zone Use Cases. My name is Nilu Parvinashtiani and I'll be helping with facilitating today's webinar. This webinar is sponsored by the Federal Highway Administration and hosted by the National Operations Center of Excellence, also known as NOCO. So we at the National Operations Center of Excellence are very grateful of the Federal Highway Administration and their support team who helped organize this CARMA webinar series. So a few logistics that I wanted to cover for this webinar was that we are recording this webinar, and that recording along with that recording will be available through the on-demand learning section of the NOCO website. All the attendee phones are on listen-only mode by default, but please stay engaged by using the question discussion pod for any comments and questions during the webinar. As those questions come to your mind, please just type them there, and throughout the webinar and especially at the end, we have dedicated time to cover the questions, and we'll be observing that question discussion pod, for your comments and questions. So just put them there, and our moderator would be covering that. So that's all I had with the logistics, and with that, I'll hand it over to our moderator, Nicole Paldo, to take this off. Nicole?
I will be your moderator today. Thank you all for being here for our Cooperative Perception ConOps for a CDA Environment webinar. We are excited to share this information with you and also get your thoughts on the topic today. Our presenters for today are Pavle Bujanovic, the Technical Manager of the Federal Highway Administration's CARMA Program Reliability Research Track, where he focuses on CDA research. We also have Sujit Racha, the ITS Manager overseeing research projects, including CARMA TSMO at the FHWA Saxon Transportation Operations Lab. We also have Yinyan Liu, an Associate Professor at Arizona State University, specializing in transportation systems modeling and analysis, specifically for connected and autonomous vehicles and ITS. And finally, we have Medha Janat, Project Manager and Senior Transportation Engineer, also at the Saxon Lab. Her experience includes research and development for traffic microsimulation software and CDA. As a reminder, we will have a question and answer session at the end of the presentation, so feel free to answer your questions in the chat pod throughout the webinar, and we will get to them at the end. And with that, I will hand it over to Sujit to get us started.
Thank you, Nicole. Good afternoon, everyone. Thank you once again for joining today's webinar. I am Sujit Racha, and I am the ITS Manager for the Federal Highways CARMA program. And I'm sure many of you are aware of this research program. So the project that we'll be discussing today, which is under this program, is Transportation System Management and Operations, TSMO use cases using CARMA. The primary goal of this project is to advance the CARMA ecosystem by enabling cooperative driving automation, which is CDA, features for the vehicles to interact with the infrastructures like traffic signals, especially at the arterial level. So also applying CDA to enhance transportation system management operations and improve safety and efficiency. So the main objective for this project is to develop concept of operations and proof of concept testing for several TSMO use cases that have been identified by the project team. One such use case or a feature that we are going to discuss today is the cooperative perception, and we would like to discuss today on developing cooperative perception use cases in CDA environment and the role that the CARMA ecosystem would play. We would also discuss the opportunities for the CARMA ecosystem to address community goals and expectations, and the functional needs and requirements for developing and deploying cooperative perception applications in the CDA environment will also be discussed. Medha Janat from Leidos and Yinyan Liu from Arizona State University are helping in developing the ConOps for this feature. and Meda and Yunyan will be talking more on the framework shortly. Pavle from FHWA, who is helping us with this research from the federal government. And Pavle will be providing an overview of a CDA and CARMA program shortly. Before we jump on to today's presentation, I would like to read the disclaimer that this presentation was created and is being co-presented by both FHWA and the contractor. The views and opinions expressed in this presentation are presenters and do not necessarily reflect those of the Federal Highway Administration or the U.S. Department of Transportation. The contents do not necessarily reflect the official policy of the U.S. DOT. With that, today, let me go over a brief agenda that we are going to discuss today. We'll start off talking with CDA and cooperative perception introductions, outline the concept of cooperative perception, and with the literature research that the team has conducted. We'll be connecting that cooperative perception and with the CARMA, how it plays a role in the CARMA ecosystem and its operational needs. After that, we will be talking about several use cases that we have identified where cooperative perception can be used effectively to improve safety and efficiency in the transportation system. We will be discussing some ongoing efforts in order to make these use cases as a proof of concept. And finally, we'll wrap up with a question and answer. With that, I will let Nicole facilitate our audience interaction question.
Hey, Sajid. So we'd just like to get a sense of the group we have with us today. Please let us know in the chat pod what organization you're coming from, your role, and generally what brings you here today. So we can take a minute to do that now. Make sure your chat pod is working and introduce yourself. Great, thanks everyone. Feel free to continue introducing yourself throughout the webinar. So Sajid, I'll hand it back over to you.
Thank you, Nicole. We will start off with introducing the concepts of CDA, which is cooperative driving automation, and the concept of cooperative perception, and then we connect these with the CARMA within the CARMA ecosystem and how it is connected, and what have we planned, the use cases or the applications that can be useful for the community here. I'll have Pavle start off with the introducing on the CDA for us.
All right, thank you so much for that. Thank you so much for that, Sajid. My name is Paolo Bujanovic. I am a technical manager here at Federal Highway, and I work with a lot of the CARMA projects that we're currently working on. So what I want to do here briefly, for those of you that may be new to CARMA and CDA, just kind of have a high-level overview of what it is. So CDA, Cooperative Driving Automation, is the idea where we want to be able to use wireless communication technology to help us be able to maximize the potential of our transportation system. So this is more than just sending out basic safety messages, BSMs. BSMs are definitely a part of that. But we want to be able to figure out how can we work as a team, how can we work as one to really make sure that every single piece of the transportation ecosystem is used to the maximum efficiency and that we're staying safe. So to that end, back last year in May, we worked with the SAE SAE Society of Automotive Engineers, and they released the J3216 standard, which is available for you to download here on this link that you can see on the left-hand side, where they define what cooperative driving automation is and how it fits into automation. So as you can see here on the top row, across the top, we have levels of automation 0 through 5, which have been around for quite a while. They were defined as part of the J3016 standard. And last year, when they released the J3216 standard, what they actually did is they defined these classes of cooperation that you see along the left-hand column. So there's 4 different classes of cooperation that you can see there. Class A is status sharing, so that's here I am and what I see. And then Class B would be intent sharing. This is where you do more than just what you're currently doing, but also you communicate what you will be doing in the near future. So maybe you might send out a trajectory for the next 5, 10, 15, 20 seconds. And when you send those out and when you receive those, it allows you potentially to be able to do some sort of clash detection, collision detection, and potentially be able to make better plans ahead of time. Then Class C is agreement seeking. This is where we actually negotiate with one another to figure out how can we do things better. So for example, if I'm merging onto a congested highway, can I negotiate with somebody to ask them to create space for me? And then lastly, Class D, that would be prescriptive. That's where we actually do as we're told. So for example, if we voluntarily choose to join a platoon, then we agree, then we have to follow by the rules of that platoon. So we have to follow the gaps that we've agreed to be a part of that platoon. We have to follow the platoon speed and things like that. So going back to Class A, status sharing, I think that's where we envision that we can actually have cooperative perception do most of its work, because we're reporting out as far as status sharing what we're currently doing and also what we're currently seeing as with our sensors. And so when we're able to send that information out to others and also receive others' information, we can help maximize the ecosystem's ability to understand its full surroundings. So with that, Ying Yang will go a little bit more into what that means for us.
Thank you, Pavle. This is Ying Yan Lo from Arizona State University. Glad to be here today. As Pavle pointed out, that cooperative perception concept is primarily under the SAE Class A, cooperative driving status sharing. I'd like to point out here in the table that under Class A, there's here I am and what I see. In principle, sharing what I see is cooperative perception. Another thing I like to point out is that this table, especially across the top, with the automated driving levels, it is very much focused on the subject vehicle that may or may not have automation. Here it sort of also implies that the level 0 vehicle does not necessarily have communication capabilities. This notion could be extended, and if level 0 automated vehicles are able to communicate and participate in cooperative perception in receiving it, in receiving the cooperative perception and for human drivers consumption, as well as retransmitting the cooperative perception information to other higher level automated vehicles in the traffic system, then they could be very valuable players in this cooperative perception concept as well. So moving on, here is an intuitive example of how cooperative perception, sharing what I see, could increase overall situational awareness. An automated vehicle could see its environment, especially the line of sight is clear and not blocked. But how would you detect objects if you do not have a clear line of sight? In this figure, we're seeing a subject vehicle, the blue vehicle, driving on the road, whereas there are other vehicles represented by the light cubes, as well as the red columns. Those could represent road users of alternative modes, such as bicyclists and pedestrians. Notice that the subject vehicle, the blue vehicle, is not able to see some of the red columns behind the largest cube on the road, which could be a heavy vehicle, a construction vehicle, or even a transit vehicle. In this case, cooperative perception could play a role in increase the blue vehicle's situational awareness. For example, other vehicles on the road shown in this figure may be able to detect and perceive these red columns, those pedestrians behind this large vehicle, and share their perceived information with the subject vehicle through vehicle-to-vehicle communication. The large vehicle itself, maybe a transit vehicle, could also have perception capabilities of its surrounding area and share its perception with the subject vehicle, again, through vehicle-to-vehicle communication. Infrastructure could be part of the cooperative perception feature as well, with sensors available, installed at the roadside that has detection and perception information capability. The infrastructure side sensors could then share its perception information to the subject vehicle through vehicle-to-infrastructure communications. So in short, cooperative perception could be incorporated in many different road users and components of the CARMA system, which we will be discussed in a little bit more details shortly, to increase situational awareness through both vehicle-to-vehicle and vehicle-to-infrastructure communication. So with that, I'd like to formally introduce the cooperative perception concept, which is sharing what I see. One of the common questions that I have heard in working on this project is, what is the difference between Cp and V2x communication? In short, cooperative perception can be considered as a specific type of V2x communication. V2x communications themselves are a broader concept where various types of messages are being transmitted, relayed. For example, the basic safety message saying, "Here I am," sent by vehicles that are automated. From infrastructure side, there could be assorted map data, the signal phasing and timing information that are being transmitted. With cooperative perception, the medium to transmit such information is through V2X and V2V and V2I communications, but the content of the information of the message being sent is the what I see, the perception information. This what I see, and if we're considering relaying information perception information generated by other automated vehicles or the infrastructure sensors, then we're also talking about improving situational awareness for all sorts of players in the transportation system. Some of the standards that are currently working on the cooperative perception concept, all of them have this consensus that essentially cooperative perception is sharing what I see. And these standards include from the SAE International J2945-8, J3224, as well as the European ETSI standards for shared perception. Cooperative perception could be very valuable in the CDA environment, especially if information is being shared about road users and other entities that may not have communication capabilities themselves, such as vulnerable road users, what we call VRUs, or vehicles that do not have automated capabilities, or they are not connected. Also, even if such vehicles are connected and automated, sometimes they could be out of communication range, and relaying perceived information of these road vehicles further upstream could enhance, again, situational awareness and contribute to both safety and mobility applications. Even in a very futuristic long-term vision where all the road users are connected, the cooperative perception message sharing could also contribute to additional data and reduce uncertainty about the perception themselves, and therefore increase the quality of perception of all the road users that are capable of detection and perception. So with that, I'd like to move on to provide an overview of existing work that has been done on the concept of cooperative perception. There are many standards that are currently being developed on cooperative perception. I'd like to start with some relevant standards, but not exactly cooperative perception. For example, the J2735, the message set dictionary for V2X. Again, as we discussed earlier, Cp is a specific type of V2X messages. Another relevant standard is the SAE J2945-9, which describes vulnerable road user safety message performance requirements, where the personal safety message, PSM, is introduced. And this PSM concept is rooted in the premise that vulnerable road users themselves could carry devices that will be able to broadcast their location and their information. So in some sense, this is the basic safety message for the pedestrian version that says, here I am. Again, Cp is sharing what I see. And such standards are being worked on currently by SAE International. Forthcoming 2945-8 deals specifically with the cooperative perception concept. ETSI recently published their report in 2019 on the shared perception, on their shared perception standards. Two noticeable prototypes are CODA collective perception messaging that has been developed and tested for pedestrian applications. Another product is a joint effort with Bosch and Siemens. Their V2X platform combines cameras and roadside units for collective perception system. And these standards and products are outcomes of a decade-long effort, at least decade-long effort, out of many major initiatives. In the United States, there's the CARMA program, the SAE efforts on relevant standards. In Europe, many major projects have looked into various aspects of a cooperative perception as well, which I'll delve into in a little bit. So the first consideration early on in the cooperative perception research is what are we sharing? What type of data to share? Is it raw sensor data or processed object data? There was some early work that focused on sharing raw sensory data and the fusion of such raw sensory data. But since then, the consensus has been that cooperative perception would be sharing processed object-based data. There's, of course, communication considerations in there, as well as computation once such information is received. And communication considerations are very tightly interconnected with security considerations as well. In fact, many, a large percentage of existing work of cooperative perception focused on the communication considerations. This varies from the content and the formats of the Cp messages to the technology, the communication technologies, to how to dynamically and adaptively generate object lists, update object lists, and how to adaptively disseminate such information as well. Once the cooperative perception message are sent and received, the receiver would then fuse the objects received to combine peer data with its own data set. And here data fusion algorithms play a huge role, and that is also one of the key technical considerations in cooperative perception. Now once that's processed, the final consideration is, what do we do with such cooperative perception? The applications of cooperative perception messages include safety as well as mobility. This could range from updating or enhancing existing automated driving systems to enhancing existing cooperative driving systems and new features, new functionalities of existing cooperative perception or cooperative driving automation, as well as even applications for human consumption for connected but non-automated vehicles. So with that, I'd like to invite Pavle to provide us an overview of the CARMA ecosystem, and from there we'll dive into how cooperative perception can be incorporated into the CARMA ecosystem.
Great. Thank you so much, Yingyan. So as Yingyan was saying, we would like to incorporate cooperative perception into the CARMA ecosystem. So for anyone who's a new member of our community, I just want to give a brief overview of what CARMA is and how we're using it. So CARMA is Federal Highway's initiative to develop open source software products that enable both us here at Federal Highway and our partners such as Yingyan and others across the country, other researchers across the country that want to be able to do CDA research, to be able to do it all as one and leverage one another's work. So to that end, what we've done is we've developed an ecosystem that has, as you see on your far left, a number of different products, some evaluation tools in the middle that you see there, and those are how we actually evaluate how good are our products, how well are we able to to transform our transportation system. And then lastly, over on the right-hand side, you see some engagement tools. So this is basically how do we make sure that we're collaborating across industry, across different researchers to make sure that we're not doing double work, but that we're leveraging one another's findings and promoting it well. So with that, over on the left-hand side, as you guys see the products, this is where we do the actual software development. So we have CARMA Cloud. Obviously, that's a piece that sits in the cloud. We have CARMA Platform, which is the piece that sits in automated vehicles. And then we have CARMA Messenger. It's the piece that sits on non-automated vehicles but allows them to partake in CDA. So for example, a fire truck is still human-driven but wants to be able to communicate with others around it. And then lastly, we have CARMA Streets. And so CARMA Streets is the piece that sits on infrastructure and allows us to cooperate with infrastructure. And so I think Medha next will tell us how we envision that cooperative perception can fit into this ecosystem.
So let me dive in a little bit deeper here into the role of cooperative perception in the CARMA ecosystem before I hand over to Meta to discuss the potential use cases. So as Pavle pointed out, on the left-hand side, we have 4 main products in the CARMA ecosystem, and you see 3 of them are boxed: the platform, messenger, and streets. And these are components of the CARMA ecosystem where we see cooperative perception can be incorporated, can be readily incorporated. And these three products are further boxed in the bottom half of the figure. But this figure is a little busy, so this one might provide a clearer overview of that. So we have CARMA platform, again, a piece of software that is a piece of automated driving software that runs on vehicles. And such vehicles equipped with CARMA platform are capable of automated driving, including obviously detection and perception of roadway objects. And they could share their perceived information, list of objects and their attributes with vehicles equipped with only CARMA Messenger. Those are vehicles that are capable of V2x communication, but do not have automated driving capabilities. At the same time, vehicles equipped with CARMA platform could also share their perceived list of objects with CARMA Streets, a piece of software that resides on roadside units that could enable cooperated driving among various vehicles approaching, for example, an intersection. Streets and platform, as well as messenger, all of them can relay information among each other. And on the infrastructure side, CARMA Streets could potentially produce cooperative perception information using roadside-based sensors. So now that we've seen where cooperative perception could be integrated into the CARMA ecosystem, this next slide, this big table, describes at a very high level what are some of the operational needs for each of the CARMA components that are relevant. So on the left-hand side, the very first column, there are 4 components listed: CARMA platform, CARMA messenger, CARMA streets, and together with CARMA streets, the infrastructure side sensors. And across the top of this table, you see 5 categories for operational needs. In fact, those correspond to the 5 major technical considerations that we have summarized earlier in the literature review section. They are enhanced object detection and perception, communication, cybersecurity, data fusion, as well as the application of Cp information. So with object detection and perception, that would be CARMA platform and CARMA streets, or infrastructure-based sensors, depending on whether such sensors are capable of computing and processing raw stream data to generate object-based content. Communications, CARMA platform, CARMA messenger, and CARMA streets are all capable of V2x communications, and they need to be able to store, broadcast, receive, and retransmit the object-based perception data. And of course here, the rules of generation for such messages, rules of updating objects in the list, rules of how frequently such messages should be disseminated, those are in fact at the moment still open research questions and are likely to be application specific. Cybersecurity, across the board, all the components should have proper cybersecurity platforms and strategies. Again, relatively open research question here. Data fusion, CARMA platform and CARMA streets, as well as CARMA messenger, should be able to combine perception information from multiple sources and merge into the local world view for local applications. So data fusion algorithms could be at various levels, could be object-based data fusion. There's object attributes, as well as part of the underlying features that led to the object detection and perception, if that is also shared, then could be feature level data fusion could also be a possibility. And finally, on the last column, we have CP application, relevant for CARMA platform, relevant automated driving systems, and cooperative automated driving systems. Such features could be updated to effectively use the CP message. In fact, that is one of the findings for one of the research projects that is carried out, that was carried out recently. On the messenger side, since vehicles equipped with CARMA messenger only are human-driven, for the cooperative perception message or data to be useful, then applications geared toward human consumption should be developed. Finally, on the street side, again, CDA applications are being implemented in CARMA streets, and such applications could be enhanced to more effectively use the CP messages. So again, a lot of the technical considerations as well as benefits of CP could be very application specific. So on that note, I'd like to invite Meta to provide an overview of possible use cases that we have identified for CP.
Thank you, Union. So as Union mentioned, that we have identified multiple use cases where CP can enhance the situational awareness and overall safety and operational reliability for the vehicle stream in the infrastructure. So the use cases that we have identified, we have categorized those into multiple applications. So this is a part of the use case table that we have developed. So as you can see that one of the use case categories, we found that vulnerable road users. So for them, when they are sharing the roadway with a vehicle that we categorize under basic road segment scenario, over there, the cooperative perception can greatly enhance the situational awareness of the vehicles who are sharing the roadway with the VRUs on the same side. Under VRU, we have also identified multiple other scenarios, for example, like control crossing areas, the non-signalized intersection, that is mid-block, where VRUs are very vulnerable over the non-signalized intersection. Boarding or alighting transit. So that is another use case where we think that cooperative perception can greatly enhance the situational awareness of the vehicles in the vicinity and also enhance the safety of the VRUs boarding or alighting from transit. We will give you an example scenario from each category of use cases in the following slides, but here I wanted to give you an overview of the overall use case category that we have developed for where CP can help. Collision avoidance is another scenario where we think that CP can greatly enhance the situational awareness and enhance safety. Just to let you know that in car following scenarios here, by collision avoidance, we are referring the ADS feature where vehicles can take immediate action, for example, like braking automatically when there is an imminent collision to avoid that. So under that scenario, we have talked about the car following scenarios and also the wrong way driving, and we will give you an example of that in our following slides as well. The other two application or the use case categorization we could think of is the conflict avoidance and cooperative driving. So scenarios under that, we found that the intersections where we have most conflict areas, the business access areas, for example, like when vehicles are coming out of a driveway in a business areas and has a potential conflict with oncoming traffic and also have limited line of sight. The two-lane two-way road where vehicles are trying to overtake with the opposing traffic. So that is another scenario where cooperative perception can help in addition to the lane changing scenarios. And then finally, the other cases were categorized under general enhanced situational awareness. And over here, where the vehicle's line of sight is limited due to, for example, like horizontal curves or a large vehicles which is in front of the vehicle during adverse weather where we have limited visibility, and also during work zone where there is a closed lane segment ahead and the vehicles may not be aware of that closed lane and can create potential bottlenecks. So those are the areas where we found that cooperative perception can help by informing driver in advance of the upcoming situation so that drivers can take potential measures as needed with that advanced information of the upcoming roadway. With that, I would like to present you a couple scenarios. So as we talked, the first categorization, we talked about the vulnerable road users. So over here, we are talking about controlled conflict areas and a crossing. So it can be pedestrian crossing, intersections, or roundabouts. As you can see, we are presenting a scenario where you can see that a northbound vehicle, which is waiting to turn right on red at the signalized intersection. And then the driver can pay most of its attention to the eastbound vehicular traffic and may not notice the VRU at all that is moving towards the vehicle on the, as you see, on the east-west direction or east-west crossing. Here, the vehicle could be made aware of the pedestrian if it is equipped with communication capabilities, as well as CP features can also inform the drivers about the pedestrian and increase its awareness. As you can see, like 3 vehicles here can detect and perceive the pedestrian, which is represented by these yellow triangles. And then these vehicles can share their perception about the presence of VRUs at the pedestrian with the northbound right turn vehicle using the V2V and V2x communication, as you can see through the green arrows. So this is how the other vehicles who can detect and perceive the pedestrian can share their information with the vehicle who has limited line of sight and limited situational awareness of the VRUs, and can enhance the safety of VRUs through sharing, through CP, I should say here in this case. The following example is about VRUs when they are boarding or alighting a transit vehicle. As you can see here, a transit vehicle is stopped for passengers boarding or alighting. And it is possible that some of the passengers would try to cross the road to catch the transit or right after they have disembarked from the transit vehicle. The other vehicle in the vicinity that should be aware of the VRUs in order to avoid potential collisions. So CP in this case can enhance such awareness and with the vehicles that has limited line of sight in this complex scenarios. This is an example of collision avoidance that we discussed earlier. So in this example, we are talking about the wrong way driving, where a vehicle enters the highway from a right-of-way off-ramp. Here you can see. CP can enhance the safety through V2V and V2I communication in such scenario where vehicle going to the wrong way to an oncoming vehicle, which is intending to take the exit. The infrastructure-based sensors like radar or LiDAR can detect the oncoming vehicle and also the wrong way vehicle and communicate that information and the overall perception of the scenarios to all the vehicles in that traffic environment, including the wrong way vehicle. So this way, the overall like situational awareness and overall perception of the traffic scenario can be communicated with the vehicles in the vicinity that may have a that can pose a potential conflict to other vehicles. This is an example of intersection where we can see that there is a large number of conflict points across various movements in this intersection. So and as you know that at signalized intersections, conflicts that exist between turning movements and associated conflicting vehicles. As you can see in this vehicle, in this scenario, the permitted left turn movement conflicts with the opposing through movement, and the right turn on red can conflict with a through movement heading towards the same departure lane. In this scenario that we are showing that the northbound and southbound left turn vehicles during the permitted left turn may have their views of the opposing through vehicles that is blocked by each other. The permitted left turn could be made safer if the turning vehicles are provided with traffic information that CP can provide. And also, we also provided a roadside unit, as you can see here, that can also detect the vehicles, turning vehicles, and communicate that information to the other vehicles here that is intended to turning left or right. So at intersection, we have multiple conflict points over here. CP communicated through other vehicles, and also, as you can see, the infrastructure unit can enhance the situational awareness of the overall intersection areas and the other vehicles here as well. So this is an example of two-lane, two-way roads when vehicles are trying to overtake in the opposing direction to use the other lane. Such maneuvers are subject to relative high risk as it requires overtaking vehicles to accurately estimate the amount of time that it would need to drive in the opposing direction, and also the distance to any oncoming vehicle in the opposite direction. The line of sight of the overtaking vehicle is generally obstructed by the immediate downstream vehicle, as you can see here. So cooperative perception here together with V2P communication can help facilitate safe overtaking maneuver in this scenario. This describes the other scenarios where CP can enhance the situational awareness in other cases. As you can see that a vehicle's line of sight, it is limited due to the roadway geometry. Although roadway geometry design guidelines ensure sufficient stopping sight distance for nominal conditions, but limited line of sight here can potentially lead to critical situations in particular edge cases. And by edge cases, we are referring that vehicles traveling above speed limit or adverse surface condition, or even like in this case, an unexpected object in the middle of the road. So in this case, CP can enhance the perception range of the equipped vehicles, and also can help the vehicle to take proactive measures to avoid potential conflicts, and also enable more effective path planning in advance so that they can avoid the conflict. All those use cases have been summarized in our ConOps that have been developed. And if you need more information, we can certainly share that ConOps with you to give you more detailed information on each of those use cases. With that, I would hand it over to Nicole to have the audience here.
Thanks, Neha. So now that you've all seen in more detail these use cases that are being developed, it's helpful for us to get your feedback on the use cases and hear any opportunities to enhance our efforts in cooperative perception. So we'd like to pause here and take a moment for you to put your comments in the chat pod, particularly about which use cases seemed most important to you, and if there are any use cases that we did not review here that we should consider exploring in the future. So just as a review, we talked about use cases for VRUs, for collision avoidance, conflict avoidance in cooperative driving, general enhanced situational awareness. So I'll flip through these so you can reference these as you're thinking through, but let's just take a minute to do that. Great, thank you. We're getting a lot of good questions and responses. We can address some of these at the end during the Q&A session, and these will be helpful as we continue to develop these use cases. So I will hand it back to Yin to talk about some ongoing efforts.
Thank you, Nicole. So our ongoing efforts currently are focused on developing CP prototype for a specific scenario for demonstration. And the scenario that is selected involves multiple users from various transportation groups, as shown here in this slide, where we have a pedestrian crossing the road. There's infrastructure side sensors. 2 vehicles are stopped at the stop line. The first vehicle at the stop line is a large vehicle, could be a heavy vehicle, could be a transit vehicle. And the second vehicle stopped on this approach is a passenger vehicle, and its line of sight of the pedestrian is in fact blocked. So for this, to demonstrate cooperative perception, the current work is to develop algorithms for infrastructure-based perception, as well as sharing of that perception message from CARMA streets to the passenger vehicle that is behind the heavy vehicle, so that the passenger vehicle becomes aware of pedestrian crossing the intersection. So that's the specific scenario selected for developing proof of concept. And this is a very basic proof of concept. And in the future, this particular scenario could be enhanced by introducing additional elements of cooperative perception. In this page, you see that the heavy vehicle is now also detecting and perceiving the pedestrian, and at the same time transmitting its perception information to the passenger vehicle. And to take that one step further, this use case, building upon the previous 2, is where it is one of the edge cases where we may have a very slow pedestrian crossing the intersection, and did not clear the intersection when the large vehicle and the passenger vehicle have right-of-way to start pass through the intersection. Whereas the heavy vehicle itself may still be stopped at the stop line because it is able to see the pedestrian. The passenger vehicle approaching the heavy vehicle is not aware of the pedestrian, and since this passenger vehicle has the right-of-way, it may take actions to change lane and pass through the intersection on the right-hand side lane. So in this application, then the shared cooperative perception message from both the heavy vehicle as well as the infrastructure side will be processed by the passenger vehicle approaching the heavy vehicle, and its trajectory will be adjusted to avoid conflict, avoid collision with the pedestrian. So that wraps up our presentation today. I would like to hand over to Sujit to provide some general information about CARMA program.
Thank you, Yin. Before we jump onto the question and answer session, I see a lot of questions, good questions that are popping up on the chat part here. We are going to address them during that session, but before that, let me provide you with some very useful resources and programs that we are having under CARMA. First, I want to talk about the CARMA Collaborative program. This is a collaborative environment that has been established to work especially with the academic institutions to conduct research and testing while providing active community of users advancing the cooperative driving automation. So you can contact anytime to us at CARMA@dot.gov with any questions related to the CDA research and CARMA. Those shall be answered by our CARMA team members. Like you see on the right-hand side of this slide, we have collaborated with so many academic institutions, and as you see the stars on the map here, several of the stakeholders and from the different institutions are collaborating with us to move this program forward and research forward, and it's happening as one collaborative effort, like Pavle has mentioned in the beginning. In addition to that, we also have a support services program where you can contact us via email from CARMA@dot.gov with any questions related to the research and how you plan, if you plan on using this any of this technology to move forward with the research path that you are carrying in your institutions or labs or the universities. Feel free to contact us at CARMA@dot.gov, and our team members will be able to help you answering any questions related to the program. We also have several very useful links that outlines with what the program is, and GitHub repository, a link for downloading the CARMA software, and some conference pages where we outline different pieces of the program, talking about the ongoing work, and also some applications that have been already deployed, and some of them which are tested and integrated as we are speaking right now. All these web links are provided under CARMA web links on the right-hand side of your window for you to utilize. With that, I will have Nicole facilitate the question and answers, and you all can keep typing in your questions in the chat pod, and we'll try to pick them up and answer as many as possible.
Thanks, Ajit. I think we can start with some of the questions and comments we got when we were asking about input on the use cases. So this one is kind of a two-part question. How do you plan to address the data reliability issue, and how do you plan to share the raw sensor data given the huge amount of data?
I can jump on to answer that. In the current consensus, raw sensor data is not being shared for cooperative perception. Cooperative perception is largely object-based messages, object-based perception messages. As far as message redundancy, very basic version of cooperative perception message sharing could have various entities transmitting their perceived object lists every 10 hertz, so every 0.1 seconds, just as the basic safety message. And this will create a large communication load if there are many components in the system that are transmitting. But on the other hand, it will provide data redundancy in that sense. So there is definitely a balance. So I do see some questions leading into data reliability as well as a communication delay. So there is a balance between communication load and the reliability of such information. And that's in fact a large key consideration in cooperative perception, and that is the communication issue. Many methods have been proposed to adaptively disseminate messages based on the
well, based on many factors. One of them could be communication load of the communication network itself. So some of the existing work would propose entities monitor the load of the communication channels and potentially use different channels or reduce the frequency of sending messages out. There are other work that have proposed only updating objects that have moved a certain distance within given time. Otherwise, they will not be updated, and their information will not be sent out to other entities in the environment. There are also distance-based. There's also distance-based methods, and some research has found that sharing information about objects that are further out in a subject vehicle's communication range would benefit other vehicles better. I would again point, and these are all great questions, and we have conducted a pretty thorough literature review on these issues, and those are summarized in our ConOps report that will be hopefully published very soon. So I'll stop here and hand over to Nicole.
Great, thanks. Our next question is, are the proposed use cases identified based on accident statistics, envisioned needs for cooperative automated driving, or something else?
So I would say both, because we have looked at who are the most vulnerable road users and the number of crashes that occur every year. In addition to the cooperative automated driving, at our section lab we are doing the CDA research, and we wanted to identify what could be the most beneficial points for cooperative perception. So this is a very great question. We have looked in both options.
Great. Our next question is, what are the software products and which standards are the software products and research based on?
So for CP specifically, there's currently only one standard that has been published, which is the ETSI, the European standards. And even within the European standards, as far as the communication frequency generation rules, there is no set method that is recommended. The ETSI standards actually also provided an overview of multiple methods that are possible, and depending on the application and the environment where the application is being implemented, the traffic density and such, and the actual needs of the application in terms of latency and et cetera, that is again a case-by-case open research question. So for this particular proof of concept that we're currently working on, the idea is to start with simple rules for communication, and as part of the research, we would monitor and monitor the communication performance and develop more advanced communication protocols moving forward.
Great. Our next question is, can you talk a little bit more about the simulation platform that CARMA uses, and also which ITS stack is used in this research?
I can take a stab at this. I am not sure about the simulation platform.
CARMA, oh, are we talking about the simulation in the CARMA ecosystem? If that is the case, so the CARMA products, the 4 products, the cloud, platform, messenger, and streets, they are software, open source software developed for different components of the transportation system, and they are not simulation. The CARMA platform is a piece of automated driving system for vehicles, etc. But there is a simulation in the evaluation where there is, in fact, ongoing work to incorporate, to combine various simulation tools in a co-simulation environment. These include CARMA, NS3 for communications, and a few others that are used.
Great. I think we have kind of a second part to that question. Can these simulations be used to evaluate the driver's reaction or human in the loop to the CARMA messenger or use cases mentioned in a driving simulator?
I think currently the simulation and the co-simulation environment does not necessarily have a human in the loop capability. There at the FHWA Turner Fairbanks Research Center, there is a driver simulator, and I do not know if there are plans to integrate that into the CDA research, although it would be logical to do so, given that especially for safety-related applications for CP, VRU is a huge player. There is one study in the literature that has evaluated human behaviors. In that case, it was actually human drivers, not human pedestrians. So human drivers, and their consumption of the perception message shared with them by other entities on the road. And I believe that study was performed using a driver simulator.
Yes, Inian, thank you for the question. As Inian mentioned, currently we do not do that, but we have plans to do that with driving simulator and with the color simulation in future. So we are planning of that.
Great. Well, I don't see any more questions coming in. Hopefully we got to address most of the questions that you all had. So if there are no more questions, I'd just like to thank everybody for joining or participating today. This is a great group. So if you want to learn more or reach out to us, please use the CARMA web links on your screen to find more information, or email us at carma@dot.gov with any further suggestions or comments or questions.